All right. Greetings, YouTube. Beautiful Mind here. So this will serve as the last lecture for the material that's required for our Calculus 1 course. So we're only going to be responsible for up to section, I think we did basically from the beginning through section 5.3. We did nearly all of those sections. As I was kind of like looking over today's lecture, I wish I had gone through section 4.9. I might go back and take a look at section 4.9. You won't be responsible for it, but I think that it would serve us to talk about that. Section 4.9 was on antiderivatives. But I think that's the one we would have done this week, but because we were short on time, I wanted to at least get into section 5.1 with integration. But yeah. So today, let me see if there are any announcements. So we're kind of entering the home stretch. This is the last of the material that we're responsible for with section 5.3, the fundamental theorem of calculus. On Moodle, just be sure that we've completed a participation and honesty quiz. I think that the student surveys are up, so just be sure to go ahead and submit those. Let's see. Participation and honesty quiz, the assessment on Moodle, and then just submit our assignments on Pearson. I think the final exam has been up for about a week, okay? All assignments are due not this Saturday, but next Saturday, May 16th. And then you can actually work on the final up until Monday, May 18th until about 3 p.m., okay? And then it'll lock out. But yeah, I'm available if you have questions. You guys seem like you guys are getting it. I can see where you've been working for the most part. I do need to sit down and go through and update. I updated the grade book this past Saturday. I kind of want to wait until this Saturday, update the grade book, and then, submit any kind of withdrawals or anything if I can. I don't know. I probably should do that sooner. I think the deadline was pushed back, but that's none of your concern. Yeah, I can't think of anything else. So I'm just gonna take some time and go through this section 5.3. Let me make sure something real quick. Okay. All right. Okay, that's cool. I didn't realize that would happen. That's cool. So, this is section 5.3, the fundamental theorem of calculus. And let's just take a moment to look at this. So let's see. So evaluating definite integrals using limits of Riemann sums as described in section 5.2 is usually not possible or practical. So I think in section 5.2, we had graphs and we would break them up into subintervals and then find the area of each rectangle and then add up the sum of the areas. Unfortunately, there is a powerful and practical method for evaluating definite integrals, which is developed in this section. Along the way, we'll discover the inverse relationship between differentiation and integration, expressed in the most important result of calculus, the fundamental theorem of calculus. The first step in this process is to introduce the area functions as first seen in section 1.2. Okay, I was just thinking if there's anything I wanted to say on that. So area functions. The concept of an area function is crucial to the discussion about the connection between derivatives and integrals. We start with the continuous function y equals f of t defined for t greater than or equal to a, where a is a fixed number. The area function of f with the left endpoint a is denoted by a of x. It gives the net area of the region bound by the graph f and the t-axis between t equals a and t equals x. Okay, so let's see this image to the side here. The net area of this region is also given by the definite integral, right? So the area function is going to be a function that describes the area bound between this fixed point a, so a is some fixed number, and our variable x, right? Where's that part? So notice that x is the upper limit of the integral and the independent variable of the area function. So as x changes, the net area under the curve also change, okay? Because the symbol x is already used in the independent variable for a, we need to choose another symbol for the variable of integration. So any symbol except x can be used because it's a dummy variable. Okay, we have chosen t as the integration variable. Okay. So because the area function is going to change as x changes, we needed another variable when we look at the integral. So that's why they chose t as a dummy variable. So like if we're going to integrate from a to x, we did f of t dt, so t was just our variable of integration. let's see here. So say we have a curve and we're considering the interval from A to B, then the area is going to be given, the area under the curve between the curve and the t-axis between A and B is going to be given by this, right? Say we looked at the area from A to C. So A of C is where the left endpoint is A, is going to give us the area under the curve between A and C of the function f. Is going to give us the area under the function f between f and the t-axis between A and C. Okay. So then we can graph those results, right? Let me see. So if we do A of A, right, that area is going to be 0. I think that came from the last section, table 5.4. So the integration from one point to itself, that the area under that curve is going to be 0. From A to B, the value of the net area appear on the graph of the area function. Okay, so that the integral, the area under the curve, the integral from A to B, that value point is here. So you have B comma whatever the answer was. So if we're graphing those results, and then from A to C gave us the most. And then notice that once the function went negative and we were getting the net area under the curve, the net value of integration or whatever. So we have this value minus this value. So that means that that area value is going to start decreasing and it's going to start to come down. So this figure shows how the area function varies with respect to x. Notice that the area function is 0 as when we did A of A, and then when x is greater than A, the net area increase, and then the net area increases as x goes from A to C. And then when x was greater than C, f was negative, which would produce a negative contribution to the area function. Okay, so let's look at this. So we have this definition of an area function. Let f be a continuous function where t is greater than or equal to a. The area function for f with the left endpoint a is going to be given by this. Okay, area function is going to be the integral from this fixed point a to some variable x of f of t dt, where x is greater than or equal to a. And the area function gives the net area of the region bound by the graph of f and the t-axis on the interval from a to x, the closed interval a to x. Okay, so hopefully that makes sense. Again, you guys should be asking questions if anything is not clear, but you seem like you're finding your way. So I'm not gonna, I let it be for right now. I probably won't go through all of these examples. I think that the main thing that I really wanted to look at was the anti-differentiation in 4.9. We did skip over it because of time. I did want to get into chapter 5 because this is week 7. So we have pretty much a week and a half remaining after this. So it was I might go back and do a video lecture on section 4.9. But yeah, you're not responsible for it, but it's kind of inherent, because math by default is cumulative. So even though I don't specifically ask questions from 4.9, if I ask questions from 5.1, 5.2 or something like that, it's going to use 4.9, right? By default. So that's just the nature of mathematics. But it's not intuitive. I probably will take some time to go ahead and do a lecture on 4.9, but I won't ask you questions directly from 4.9, but it doesn't hurt to look at it. But let's keep going. So in this example, it says that the graph of f is shown in figure 5.37 with areas of various regions marked. Let a of x be this integral and let f of x be this integral. Okay. Be two area functions for f. Note the different left endpoints. Okay. Evaluate the following area functions, a of 3 and f of 3. Okay. So we have this graph over here to the left, okay? And so we'll be using this to work through this example. So let's do like this. I usually like my paper. Okay, and we're gonna go here. We use blank for now. So for example 1a, we're asked to find a of 3 and f of 3. Okay, let me move this down a little bit. The function, we're given that a of x is going to be the integral from -1 to x of f of t dt. And f of x is going to be the integral from 3 to x of f of t dt. So these are just two different area functions for the same function. And we have noticed that we have two different left endpoints for these two area functions, okay? So let's take a look at a of 3. So then a of 3 is going to be the integral from -1 to 3 of f of t dt, okay? So if we look at this graph here, as we go from -1 to 3, we see that that area is -27, right? Remember, because it's below the x-axis. So that one is just going to be -27. I just pulled that straight from the graph, right? I think that's okay. Then let's look at the area function f of 3, which is going to be the integral from 3 to 3 of f of t dt. I think from last class, this is from table, I think it's table 5.4. The integral from 3 to 3 from a number to itself, that the area under that curve is going to be 0. All right. Let's see something. Okay, so they did want to make a note. And then I'm just going to say notice that if we did a of 3 minus f of 3, that result's going to be -27, right? That's just an observation, okay? So then let's look at example 1b. Example 1b, a of 5 and f of 5. A of 5 and f of 5, okay? So then a of 5 is going to be the integral from -1 to 3 of f of t dt, okay? So, sorry, not -1 to 3, but -1 to 5 of f of t dt. So if we go back here to the graph, from -1 to 5, so we have to say 3 minus 27, right? Because the positive contribution to the area was 3, the negative contribution was 27. So then that one we got to say 3 minus 27, which is going to be -24, right? Then if we consider the area function f of 5, that's going to be the integral from 3 to 5 of f of t dt. So then looking back at the graph, from 3 to 5, we see that that area is 3. Okay, that one's going to be 3. So then if we consider a of 5 minus f of 5, that's going to be the -24 minus 3, which is -27. Okay, again, it's just an observation, but you should start to notice a similarity. And then for part 3, 9 and 9, right? So for example 1c, we're asked to compare a of 9 and f of 9 for these two area functions. So then a of 9 is going to be the integral from -1 to 9 f of t dt, okay? So then if we look back at the graph, so from -1 to 9, we're going to have to do 3 minus 27 minus 35. So that's going to be 3 minus 27 minus 35. 62, so 59. 59, I think that's what I got there. And then if we do f of 9, that's going to be the integral from 3 to 9 f of t dt. So from 3 to 9 is going to be 3 minus 35. negative 32, right? So then if we consider a of 9 minus f of 9, that's going to be negative 59 minus a negative 32. So then that's going to be, it should be negative 27, right? It should be the net difference. Okay. So I think that these results are fine. Let's see. I'm just going to use this at this point. Let's go like this. So like if we compare, the value of a of 3 is going to be the integral from negative 1 is going to be the integral from negative 1 to 3 of f of t, is the net area of the region bound by the graph from negative 1 to 3. Using the graph, we see that this is going to be negative 27. Okay. But then when we do from 3 to 3, that the area under that curve is going to be 0 by property 1 in table 5.4. That's from last class, right? So then as an observation, notice that a of 3 minus f of 3 is negative 27. And then for this one, I think we got the negative 24. We also got the 3. And then notice that the difference between these two is still negative 27. And then this one was negative 59, negative 32, and the difference was still negative 27. So example 1 illustrates the important fact to be explained shortly, that two area functions of the same function differ by a constant. Okay, so that was the point that was driven home when we compare the area functions, two different area functions of the same original function, they differ by a constant. Okay. So then let's look at this example 2. Now we're going to consider the area of a trapezoid. Consider a trapezoid bound by the line f of x equals 2x plus 3 and the t-axis, where t goes from 2 to x. Okay. The area function a of x is going to be given by the integral from 2 to x of f of t dt. This gives the area of the trapezoid for x greater than or equal to 2. Evaluate a of 2, evaluate a of 5, find and graph the area function y equals a of x for x greater than or equal to 2, okay? And then compare the derivative of a to f, okay? Let's see, so we have an image over here that we can use. So we have this line, f of t equals 2t plus 3, right? And we want to consider the area bound by, as the function goes from 2 to x, right? In this fashion, okay? So the area of a trapezoid is going to be 1/2 the height times base 1 plus base 2, the two parallel bases, right? Evaluate a of 2. Okay, let's do it like this. Paper. Okay. So for example 2a, we're asked to find a of 2. So then a of 2 is going to be the integral from 2 to 2 of f of t dt, right? But if we integrate from a number back to itself, that should be 0, right? So I'm gonna let that be the area under the curve at that point is going to be 0, all right? So then let's look at example 2b. Onto the next part, we're actually look at a of 5. Okay, a of 5 is going to be the integral from 2 to 5 of f of t dt, right? So that's going to be the area under the curve as x goes from 2 to 5, right? Or the line, right? But because it's a trapezoid, if we want the area of a trapezoid, that's going to be 1/2 the height. So in this case, the parallel lines are vertical. So the height is given on the x-axis. That's going to be what? 5 minus 2. So in this case, the height is going to be 5 minus 2 times base 1 plus base 2, right? So base 1 is going to be what? F of 2 plus f of 5, right? I'm just directly applying the formula for area of a trapezoid, okay? So then if we keep going, let's see. This is going to be 1/2 times 3. F of 2 4 plus 3 is 7, plus 10 plus 3 is 13. What is that going to be? 20 divided by 2, 10, which is 30. 30. Let me see. That was part B, right? I'm going to go with this answer for now. Give me just a moment. Sorry about that. I had to sneeze and I didn't want to like blow your ears out. Yeah. All right. So we're back. I'm watching the clock as well. Okay. All right. So I'm going to go with these. Okay. So let's look at part C. Let's add a page. So again, I'm not going to go through all the examples. They definitely get a little intense towards the end. If you need me to or want me to, I'll probably do a separate video and like go into the details of probably like that last example. But we'll just take some time to go through some of these. Let's look at example 2C. Okay. 2C asks us to find and graph the area function y equals a of x for x greater than or equal to 2. Okay. So they want us to find the area a of x. It's going to be the integral from 2 to x of f of t dt. But then if the basis shape is a trapezoid, area of a trapezoid is going to be 1/2. The height in this case was going to be, it was x minus 2, right? The x-axis, the length along the x-axis, times, we're going to add those two bases together. So we're going to say f of 2 plus f of x. Okay. I'm going to create some space by moving over here. This is going to become 1/2. We got our x minus 2. F of 2, 4 plus 3 is 7. That's going to be 7 plus f of x it's going to be 2x plus 3. 2x plus 3, all right? So if we keep going, we got 1/2. We got this x minus 2. We have this 2x plus 10. I'm going to go ahead and distribute that half. We'll get x minus 2, x plus 5. And then this will expand to x squared plus 3x minus 10. I think this is good. For x greater than or equal to 2. So then our a of x should be x squared plus 3x minus 10 for x greater than or equal to 2. Let's see. So what is it? A parabola with a y-intercept. Oh man, I don't know what that was. Upward facing parabola with a y-intercept of -10, and we could find like the actual vertex. We could even use the vertex formula, negative b over 2a. So the vertex occurs when x is -3, so that you can find the corresponding y. Okay, so we can graph this quadratic. I'm not going to do that right now. but I'm going to go with this answer. Okay, let's see what else we got. Compare the derivative of a to f. Okay, so if our claim is that this is our area function, so then example 2D. So if we look at the derivative of this area function, that's going to be 2x plus 3, which should be equal to f of, what is it? Compare it to, which is f of x. Okay, I'm going to just say it's f of x, which is what it's supposed to be, right? 2x plus 3. 2x plus 3. Okay. So let's see, how do we do? 0, 30, and all of this. Let me see. 0, 30 is fine. X squared plus 3x minus 10. Okay, I didn't write everything that I needed to. That's fine. Yeah, that's fine. I'm gonna let it be. Okay, let's see. We still got a ways to go. So now let's see if we can develop this. How well we can develop this notion. Okay. So example 2 suggests that the area function a for a linear function f is an antiderivative of f. That is, that the derivative of the area function gives us the original function. Our goal is to show that this conjecture holds for more general functions. So we found the area function of an image of a shape that we already knew the area of. But then, like, what if we have a function where we don't? It's not a general basic shape, right? Assume f is a continuous function defined on the interval a b as before. The area function is going to be given by the integral from a to x of f of t dt. Again, it's going to be the area function for f with the left endpoint of a. It gives the net area of the region bound between the graph of f and the t-axis on the interval from a to x for x greater than or equal to a. Okay, so we have some function. We have some function y equals f of t. The area function. Now we're going to consider the area function of x plus a of x plus h, right? So from a to here, a to x plus h. So we have this area function. Then this one this is the area function for x plus h. This is the area function for x. So the area created by the graph between a to x here, right? And our claim is that this is approximately going to be h times f of x. So this distance, if we say this, the right minus the left, is going to give us h. And again, notice that this one is approximately rectangular when h is small. Okay. H times f of x. Yeah, right? Area function, right? So if this is essentially a rectangle, so if h is really small, this shape is essentially a rectangle. The distance here on the x-axis is just h. The distance here on the y-axis is f of x. And again, for h really small, this is essentially just a rectangle. So then this area function is just going to be h times f of x. So we've developed that the area function of x plus h minus the area function of x is approximately h times f of x, again, when h is really small. So note that for h positive, a of x plus h is the net area of the region whose base is on the interval from a to x plus h. And a of x is the net area of the region whose base goes from a to x. So the difference, if we say the area function of x plus h minus the area function of x, is going to be the net area of the regions whose base is an interval. If h is small, the region in question is nearly rectangular with a base length of h and a height of f. Therefore, the net area of this region, so if we say the first area function minus the second, is approximately this, right? If the left is approximately equal to the right and h is just some constant, we can move the h to the left, right, by division. So this is what, like the difference quotient? that we had before from college algebra. So we have a of x plus h minus a of x over h is approximately f of x. Okay. So then an analogous argument can be made with h is negative, and that's fine. So now we're going to consider let h go to 0. Remember, this is for small h. Now we're going to take the limit as h tends to 0. Okay. But we just said that this expression here, a of x plus h minus a of x over h, this is really just f of x. Notice now the h is gone, so the limit as h tends to 0 is just going to be f of x. This thing on the left is the derivative of an area function using a difference quotient articulation. So we see that the derivative of the area function is going to be f of x. Because the area function is the integral of from a to x of f of t dt, the result can also be written as a prime equals d by dx of the integral, which is just f of x. So essentially what it's saying is that the derivative essentially cancels out the integral and vice versa. So I have no idea where all this mucus came from. Yeah, I didn't really. I'm trying to think if I had any animal products or dairy. I mean, and I know a lot of times they'll sneak that kind of stuff into certain things, and I know I had an urge to. I'm just momentarily reviewing like what did I eat. I'm totally just like being like super wasteful with these tissues that I have. I don't know what it is. I think I just like the sensation of pulling it from the box. All right. Anyway, these are still good, so let me not use those. Okay. All right. So we have this fundamental theorem of calculus. If f is continuous on a closed interval ab, then the area function given by a of x equals the integral from a to x of f of t dt, where a is less than or equal to x, which is less than or equal to b, is continuous on the closed interval ab and differentiable on the open interval ab. The area function satisfies a prime of x equals f of x. So the derivative of the integral is just f of x, which means that the area function of f is an antiderivative of f on the closed interval ab. Okay, let me see. So given that the area function is an antiderivative of f on ab, so yeah, right here it says, remember from section 4.9. So I know we skipped 4.9. I think I probably will do another presentation on section 4.9 just to be complete. I know we kind of went a little bit out of order, but I probably will go back and do. But you're not going to be responsible for it directly, but indirectly, when I start talking about chapter 5, you will be responsible for it. I might even load some practice there on Pearson and just say optional. So that means I won't factor it into your grade, but just make it available. Plus, you all should have books. I know you have a different book. Yeah, I'll probably just make some of these examples available on Pearson so you can get some practice with it. Okay. Any two antiderivatives of f differ by a constant. Okay, assume f is any other antiderivative. We have that antiderivative of f is going to be the area function plus some constant, right? Noting that a of a equals 0, it follows that f of b minus f of a, which is going to be a of b plus some constant minus a of a plus some constant. If you distribute the negatives, the c's should cancel. So this, by definition, is just going to be a of b, right? Because that's automatically going to go from a to b. So writing a of b in terms of a definite integral leads to a of b is going to be the integral from a to b of f of x dx, which is going to be the antiderivative of b minus f of a. We have shown that to evaluate a definite integral of f, we find any antiderivative of f, which we call a capital F, and then compute f of the antiderivative of f of b minus antiderivative of f of a. The difference in the value of f between the upper and lower limits of integration. That's fine. This process comprises the second part of the fundamental theorem of calculus. So the integral from a to b of f of x dx is going to be the antiderivative of f of b minus antiderivative of f of a. That's fine. Okay. That's a quick check. I'm going to let that be. Okay. Let me see something. 4.9, right? Anti-differentiation. So yeah, there were some shortcuts. I guess I thought that these shortcuts were going to appear in chapter 5, and I didn't really look at section 4.9. So I'm going to use some shortcuts that actually appear. I guess they appear in section 4.9. I had to go back and look and check and confirm, because that's actually what I wanted to talk about, and I didn't realize I skipped over it. So I'm definitely going to go back and go through those. Yeah. So evaluate the following definite integrals using the fundamental theorem of calculus. Interpret each result geometrically. Okay. Can I go like this? So we have example 3a. Evaluate the integrals. So we're asked to evaluate the integral from 0 to 10 of 60x minus 6x squared dx, right? So I think this should be in section 4.9. It's the shortcuts that I kept referring to, right? Now we can actually do the following. We can rewrite this in the following way. Let's see. We're going to have 60 times the integral from 0 to 10 of x dx minus 6 times the integral from 0 to 10 of x squared dx. Okay, I think that came from the last section. Okay, and then to evaluate the integral, let me give myself some more space. To evaluate the integral, we have the first property. So like for instance, if we have x to the power of 1, now for instance, if we had x squared and we were taking the derivative we will bring down the exponent and subtract 1 from the exponent. So when we go to integrate, we essentially do the reverse of that, right? So if we have x to the power of 1, now we're going to add 1 to the exponent. So the 60 just comes down. Now that's going to become x squared over, instead of multiplying by the exponent, now we're going to divide by this new exponent. Okay, it's kind of like the reverse of the differentiation. I think those details are in section 4.9, so I probably will go back, so so we can kind of be a little complete. And we want to evaluate this antiderivative from 0 to 10. All right. Okay, I think that's fine. Then we're going to say minus 6 times. For instance, if we have x squared, that's going to become x cubed over 3, evaluated from 0 to 10. Okay. So then what we do here, we're going to have 60 times 10 squared. That's going to be 50 minus 0, minus 6 times, what is that going to be? 1,000 divided by 3 minus 0. Okay. If we keep going, 30, so 3,000. 6 divided by 3 is a 2, minus 2,000 should be 1,000. Okay. Let me look at that answer because I don't think I looked at this one in advance. Yeah, 1,000 is good. Okay. Let me see this next one. Let's try the next one. Example 3b. What's the time? Example 3b. All right. This one is the integral from 4 to 16. And there are other like shortcuts. That's just the main one that we use. Let me see. 3 times the square root of x dx. 3 times the square root of x dx. Okay. Let's see. So first, we're going to start by rewriting this integral in the following way. Actually, I'm going to go ahead and we can move the constant to the front of the integral. And instead of writing the square root of x, I'm going to rewrite that as an exponential. So x to the power of a half dx. Okay. All right. Let's see. So then if we use the same technique we just did, this is going to be 3 times. So a half plus 1 becomes 3 halves. So we're going to have x to the power of 3 halves divided by 3 halves. We're going to evaluate that from 4 to 16. Okay. So then that's going to become 3 times 2/3. Let's see. That's going to be 16 to the power of 3 halves minus 4 to the power of 3 halves. Okay, so if we keep going, these cancel, we get 2. We can do the square root of 16 is what? 4. 4 to the power of 3. 16 times 4, 64. So there's going to be 64 minus, the square root of 4 is 2 to the power of 3 is 8. What is that? 56, 112. Okay, I'm just going to go ahead and check that one too. 3b. Blah, 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 112 right there. Okay. And then 3c, let's see, c. Okay, let's give it a go. I think I need some more space though. Zero to 2 pi 3 sine x dx. Example 3c. Integral from 0 to 3 pi. 0 to 3 pi. Nope. 0 to 2 pi of 3 sine x dx. 3 sine of x dx. I'm going to make sure I got that right again. 0 to 2 pi 3 sine x dx. Okay. I think I might just drop this to the next page. Oops. Okay. Let's see. So we can move, one of the properties is that we can move the constant in front. Okay. Let me think about this. We might have to break this up. If we move the constant to the front, integral from 0 to 2 pi sine x dx. So then this should be the integral of sine. Let me see. The derivative of sine is cosine. Derivative of cosine is negative sine. So it should be negative cosine of x from 0 to 2 pi. I feel like I might be oversimplifying this, but I'm gonna keep going with this and see what happens. I'm going to pull out that negative. No, I'm gonna let it stay. Yeah, I'm gonna just let it stay. So then 3 times, let me see, 2 pi, that's going to be what? So that's going to be negative 1 minus 1. Is that right? Looks like it's going to be 0, right? So that's a negative 1 minus another negative 1, double negative. So it looks like it's going to be 0. I think this actually makes sense. Because sine is odd, right? And we, like, okay. So the reason I was kind of hesitating, if we think about the graph of sine, right? And we didn't shift it left or right, we just amplified it. So this graph, so what we're doing is evaluating the area under the curve as sine goes from 0 to 2 pi of this vertical stretch, right? So if we think about the graph, let me just do a quick sketch to kind of bring to life what I'm seeing. And I guess, I don't know if this is a property or not. Let's just say, let me see, 1, 2, 3, 4. Let's make it a little bit bigger. 1, 2, 3, before. It's just as a quick sketch. So this is going to be pi over 2. This is going to be pi, 3 pi over 2, 2 pi. And say this is there, 1, 2, 3. This is 3, this is negative 3. So 3 sine of x, right? That graph is going to go from right here to here to here to here. And go away. This needs to be negative 3. This is going to be here and then here. So then the graph is this, right? I don't know if they allow curves. I could do a circle. Okay, let's just do like this. So if we think about the graph, and I'm just kind of trying to give a visualization as to why this answer makes sense. I think that used to trip me up in the past. I would get an answer like this. I was like, what? That doesn't make sense. But then now that I'm aware of this whole positive contribution to the area and the negative contribution to the area, it totally makes sense. I think that was something I used to mess up. Right? So that blue there represents the positive contribution of the contribution to the area. And then here we have the negative contribution to the area. Oh, I don't know if I get in there. I can erase, I guess. Let me erase this extra. Oh, yeah, that should be fine. Ooh, it was weird. Alright, that'll work. I ain't like that last stroke. Okay. Being meticulous for no reason. Okay. So, all we did, it was basically just the original sine function, but it was it did a vertical stretch by a factor of 3. So if the blue is a positive contribution and the green is a negative contribution, notice that sine is odd, which means it's symmetrical about the origin. So when we say the positive contribution minus the negative contribution, it should equal out to 0. So this answer makes sense. Right, so I'm gonna go with this one for this one. Did we box the others? Okay. And then D, I'm gonna write this right here. The integral from 1/16 to 1/4. We got the square root of t. Hang on. Okay. We got the square root of t minus 1 over t dt. This is what we want to work on. This is 1D. Let's give it a go. We've been doing well so far. I know, like, my last examples in the last couple of classes have just been rough. I mean, it's just like that sometimes. I think I did those on the fly. I didn't really look in advance. I was like, oh, let me look in advance this time, just so I'm not, So then, what is this? Example 3D. Okay, and let's paste. Okay, and let me just redo this guy, undo. Alright, and we get rid of that. I'm gonna rewrite this. Integral from there to there, this. Okay. Let's see. So I'm gonna actually start this one out by rewriting this integrand. We're gonna have the integral from 1/16 to 1/4. I'm going to distribute that. Since we're dividing by a monomial, we can essentially distribute. What's my time? Okay, we still got a good amount of time. So if we have t to the half minus t to the 1, that's going to become t to the negative 1/2. 1 over t to the minus 1. Let me think about that one. T to the minus 1. Okay. So this can become, I'm gonna go ahead and do the first one. If we add 1, so 1 plus a negative half becomes a positive half. Okay. So then that becomes t to the power of a half divided by a half, evaluated from 1/16 to 1/4. So normally it should be minus that part. I'm going to say the double negative makes it a positive, right? Now t to the 0. Now look, if we tried to add 1, we would have t to the 0 over 0, which we can't do, right? But 1 over t, I think, is the derivative of natural log, right? So I think that was something that we mentioned before. I think we did. But yeah, t to the minus 1, that's the derivative. So that antiderivative is going to be natural log of t, evaluated from 1 by 16 to 1 by 4. I think that's proper. Okay. My dog is so funny. She is just like splayed out. She is hilarious. Too funny. Let me see. I'm trying to think. Okay. All right, let's keep going. Let's go with this. So let me rewrite it. So this is really what? 2 times the square root of t, evaluated from 1 by 16 to 1 by 4. So if we do the natural log, and this is essentially the natural log of 1 by 4 minus the natural log of 1 by 16. Okay. We're going to come back and evaluate that. So then the square root of a fourth is a half. So that's going to be 2 times 1/2 minus 1/4. All right. So we can get that. Natural log of a quarter is the same as negative natural log of 4. So negative natural log of 4. Have to use a calculator there. Right. Yeah. And then plus, essentially, it's going to become plus the natural log of 16. So that's like log properties, okay? If we distribute that too, I'm just going to distribute it. That's going to be 1 minus 1/2 minus the natural log of 4 plus the natural log of 16, okay? And then we can crunch that number. Let me see if that's what they did. For part, let's see, C, we got 0, that's fine. Natural log absolute value. Okay. Okay, right here. They got 1 minus the natural log of a 4 minus 1/2 Let's see if we get that number. They got 8863. Let me see if I get that number. I'm probably missing some property, but I think if we just crunch our number, we'll probably get the same thing. Let me crunch my number and see what happens. Okay. Give me just a moment. I'm loading my calculator. There's the half. Oh, they're saying that's essentially 0. I'm just gonna crunch my number. So we got let's do that part right there. Reload and refresh. Okay. So I'm just gonna type all that in. 1 minus 0.5 minus the natural log of 4 plus the natural log. Oh. That's 4 squared, right? Oh, okay. I see it now. I was like, what am I missing? Let me go ahead and go a little further here. So this is going to be the same as 1/2. Now we got, let me see. Natural log of 16 is the natural log of 4 squared. So that becomes 2 times the natural log of 4. So then we have negative natural log of 4 plus 2 natural log of 4 leaves us with plus the natural log of 4, which is what they have. That's all I wanted. That's just properties of logs. Plus, let me see, we were missing something here. we got a positive. So maybe I got my signs wrong somewhere. Negative. That should have been a -4. Maybe that plus there. I think I got my signs mixed up somewhere. That minus. Maybe that's where I messed up. Because that minus is already accounted for. Okay, yeah, I think this is where I messed up. So I'm going to change this. I'll do it in red so it stands out. So this should have been minus, which means this would have been minus, which means this would have been minus. Now if we distribute our negative, this would have become a plus. This is going to be minus. Yeah, I think that's where we messed up. And then, so 1 minus 2 gives us a -1. So this would have been minus. Yeah. Okay. So then that should have been a plus natural log of 4. Right there. Plus. And then we're going to say minus the log of 16. Minus the log of 16. Okay. -0.8. Yeah. So we got it. We got stammered a little bit, but it wasn't too bad. So we got the same result. That was fun. 8863. So again, this is approximately 8863. Okay, let me see the time. Okay, let me see. How much more did I want to talk about here? Let me go ahead and turn that off. Okay, I think we did all of these. Let's look at this one. I might do one, maybe two more, because I'm getting kind of tired, and we're about out of class time. Let me see. The graph of this is shown in the figure. The region R1 bound by the curve on the interval -1, and R2 is bound by 0 to 2. Find the net area of the region between the curve and the x-axis from -1 to 2. Okay, so if we look at this graph, if we want the net area, it's going to be the area from basically the green minus the red. So I think we need the antiderivative, right? Yeah, okay, let's do that. We can do this. So let's go here, let's go paper, let's put this back. And we actually need another page. Yeah, that one, let's add a page. Okay. All right. So this is example, and I guess we can drop down to the next one. This is example 4A. So if we want the net, it's just going to be the green minus the red. Now, if we have f of x is going to be what? 6x times x plus 1 times x minus 2. So they're basically asking us to evaluate the integral from -1 to 2 of f of x dx, all right? So this is going to be the integral from -1 to 2 of this 6x times x plus 1 times this x minus 2 dx. If we keep going, I'm going to go ahead and expand those out. -1 to 2, we got this 6x. Now if we expand, that's going to be what? X squared minus 2 plus 1 is going to be minus x minus 2 dx. And then if I distribute -1 to 2, it's going to become 6x cubed minus 6x squared minus 12x dx. Okay. So then I'm going to expand these based on what we introduced last class. So we can rewrite this integral in the following way. 6 times the integral from -1 to 2 of x cubed dx minus 6 times the integral from -1 to 2 Actually, like that first one. I'm gonna just copy and paste that. Copy, paste, boom. Of x squared dx, then we could say minus 12 times the integral from -1 to 2 of x dx. So I just broke it apart into the simpler form, right? So then I think these are the anti-differentiation shortcuts that are in section 4.9. The x cubed becomes, we're going to have x to the power 4 over 4 as it goes from -1 to 2. Then we're going to have this minus 6. We're going to have x cubed over 3 as that goes from -1 to 2. And then we're going to have minus 12. We're going to have x squared over 2 as it goes from -1 to 2. Okay, if we evaluate those, that's going to be 6 times 2 times 2 is 4, 8, 16. 16 divided by 4. So that's a 4 minus 1 by 4, right? I think that's it there. 6 times 8 divided by 3. That's going to be is minus, so double negative is positive, 1/3. And that's an 8 divided by 3. Okay. Minus 12 times 4 divided by 2 is 2, minus, that's going to be positive 1/2. Okay, I think this is okay. And then we just need to crunch those numbers. Let me see. 3 3/4. 4 times 3 is 12. 15 over 4. Nine over 3 is 3. 3 by 2. 1.5, right? So 3 by 2. Okay. The 4 turns that into a 3, so that's 45 over 2 minus 18 over 1. 6 times 3. Okay. What is that? 22.5? I'm just going to do 22.5 minus, what is that? 36. So if that were 30, that would be 6 plus what? 7, so 13, 13.5. Okay, let's see, how do we do? And then find the area of the region between the curves. So then the second part is basically like taking the integral of the absolute value, because instead we don't want the net difference, we just want to we're going to say R1 plus R2. Okay, let me see if I got that one right. So this negative 13.5. 13.5 is correct, all right? Okay. So then for part B, example 4B, a nice way to summarize it is essentially what they're asking for. Let me copy this stuff here. This. Let's copy. I'm going to paste. Undo and paste. But what they're asking for here, if we want to add those two areas together, they're essentially asking for the absolute value of this guy. I'm going to use the graph because we have it. Because it's only negative. We see that from the graph that it's negative from 0 to 2. So what I'm going to do, just for I think this is the simplest way because of what we have access to. I'm going to rewrite this as, so from the integral from -1 to 0, we know that f of x is positive, so we're just going to let that be. Normally it would be plus from 0 to 2, but since we know that that's the negative contribution, do I need to introduce a negative or not? I think I do need to introduce a negative. So normally I would do plus the integral from 0 to 2, but because that should be the negative contribution, because we just did the integral from negative and it worked out, right? That gave us the net. So what I'm going to do, instead of saying plus, I'm going to say minus the integral from 0 to 2 of f of x dx, just to account for that negative contribution, right? Yeah, let's evaluate these integrals, and we should get the desired results. Because we're looking for something where it's going to be region 1 plus region 2. We're just going to add those regions together instead of subtracting them like we did before. That is a lot. Maybe I could use... Can I use something else? All right. 6x cubed minus 6x squared. Let me at least use that. I don't feel like doing this. What's the time? I'm trying to see if there's a more efficient way. All right, let's do from -1 to 0. 6x cubed minus 6x squared. 6x cubed minus 6x squared minus 12x. We said what? Minus 0 to 2, 6x cubed minus 6x squared minus 12x dx. Okay. I mean, this will get us there. I don't feel like doing it. I'm probably gonna make this. I'll probably finish this one out and leave the rest as an exercise. Let me see. Okay. I think I got a faster way. Oh, wait, is that the antiderivative? No? Yeah. Okay, let me see if I can do this a little bit faster. All right, so we're going to say equals. So that becomes 6x to the 4 over 4 minus 6x cubed over 3 minus 12x squared over 2. As it goes from -1 to 0. Okay, that doesn't look too bad. Let me add a page. Okay. Then we're going to say minus that same thing. 6x to the 4 over 4, 6x cubed over 3, 12x squared over 2. But this was going to go from 0 to 2. Okay, so we keep going. So when x is 0, all those terms are gone. We're going to say minus when x is -1. That's going to become positive there. So that finishes as 3 over 2. That's going to become double negative is positive there. That's going to be 2. It's going to stay the same. It's going to be 1, and it's going to be 6. Okay. Then we're going to say minus. Now, when x is 2, 4 times 2 is 8 times 2 is 16. Divided by 4 is 4, so that's 24. When x is 2, 8 times 3, 8 times 6. 8 times 2 is 16. Minus 24, okay? And then when it's 0, all those terms are gone, right? Okay. All right, let's see if we can get there. We crunch this. So 2 minus 6 is what? -4. Plus 1 is -3, -2.5. So double negative is positive. So I think that one is 2.5 minus 4 and 4 is 8 minus 24 is what? Negative 16. So then 18.5, 37 over 2. Let's see, how do we do? If we add those two regions together. So the first one, we got the negative 27 over 2. 37 over 2. Okay, I got a little nervous. I saw that 16. I was like, no, it's not 16. Ooh, okay, it wasn't too terribly bad. Let me see the time. Okay. Okay, I'm going to use the notes that they have provided for these just for the sake of time. Yeah. So like for this, for example here, simplify the following expression. So we're asked to take the derivative of the integral. So these should cancel each other out, right? Notice that we have the fixed point on the bottom and the variables on the top. So this form is proper. So the derivative of the integral, they're going to cancel each other out, and we're just going to get just the sine squared. Now notice in this one, the part 1 of the fundamental theorem of calculus, the fixed number needs to be on the left endpoint or on the bottom. All right. So if we have to switch these around, that means we have to introduce a negative. The negative of this, now they can cancel, and so the result is going to be negative of the integrand. Okay. And then this one, even though we have the fixed one on the bottom, usually this is an x up here, and we have x squared. So we have to do like u substitution. So let u be x squared right here. Then now we're going to be taking the derivative of the integral of u right here times the derivative of u, which is 2x. So then we apply the formula. This is just going to be cosine of u squared times 2x, and then we have to put the u back. So u squared was x squared, so then we get this. Okay. So, you know, that's the long and short of that. Let me see. Okay, these four regions have the same area. Based on the graph, do the following. Find the zeros of A of the area function from 0 to 17 of the area function. So it looks like the first one, okay, the zeros look like they occur at 0, 8, and 16, right? Because the net area. Let me see, example 6. Here it is. Here it is right here. The zeros of the area are 0, 8, and 16. Okay. Let's look at part B. I guess we don't need that page since we're not working this one. Delete the page. So then here, part B says, find the points from 0 to 17 which the area has a local max or a local min. So the area for this is some positive contribution. So like as we go here, the area, let me see, it's increasing. The max should occur here at 4, right? Then once we start introducing this negative contribution, the area is going to start going down. So a max should be here. This was a 0, so this should be a minimum. Let me see. It's going up. It reaches the climax. Coming down. Now it's at 0. So this is saying the area is going to go back up. Reaches a max, and then here it's back at 0. So there should be a max here, min here, max here, min here. So a maximum at 4. So minimum at 8 and 16, and the max at 4 and 12. Okay, so that's all. This is all just concept. Again, we're just observing how the area changes as we traverse along the t-axis, right? So here, when t is 0, the area under the curve is 0, right? As we go to the right, the area is increasing. It's still increasing up until here. So we have our maximum area here. Once we start adding this part in here, it's going to decrease. It's going to be the negative contribution to the area. So the max occurs here, and then this is going to start taking away, and then taking away, taking away, taking away, and then the sum of the area is going to be 0 back at this point. Then it goes back up, max, and then back to 0. Okay, sketch the graph of A. So it should go up, reach a max, and then come down. So I'm thinking like a zigzag. Yeah, something like, well, not a zigzag, but this. See, it reached the max and then went to 0, then max, and then 0. Okay. And I think I'm going to just let this one be. Let me think about it. Graph the sine function. Yeah, I'm gonna leave this one. That's for the sake of time. And it does get a little, whatever. We can look at it if we need to. I'm trying to see if there's anything else. Proof of the fundamental theorem. I think I do want to take a moment to look at this though. So we have this proof. Now we're just doing a read along here, and then we're gonna kind of wrap this up. Oh, that was much better. Okay. So let f be continuous on a closed interval AB, and let A be the area function with the left endpoint A. The first step is to prove that A is differentiable on the open interval AB, and that the antiderivative of the area function is equal to f of x, which is part 1 of the fundamental theorem. The proof of part 2 then follows. We assume that x is between A and B, and use the definition of the antiderivative. So the derivative of the area function is going to be, the limit as h tends to 0 of a of x plus h minus a of x over h. That's fine. Assume that h is positive. Use figures 5.52 and property 5. Okay. So then there's a of x plus h minus a of x. That's going to be the integral as a tends to x plus h. So the first part is the integral as a tends to x plus h of f of t dt minus the integral as from a to x of f of t dt. Okay. Let's see. X, all right? Okay, so in a graphical sense, that line there that we just went through, so this line here, this minus this, so if we're saying from here to here minus from here to here, what we're going to be left with is from here to here, which is just h, all right? This goes from x to x plus h right here. So the integral from x to x plus h of f of t dt. So that is, this expression is the net area of the region bound by the curve from x to x plus h. Okay, that's going to be this part here. Okay. So then let little m and big M be the min and max values of f on this interval respectively, which exist by the continuity of f. Therefore, m is going to be less than or equal to all f of x. This looks like the squeeze theorem. Let's see. Which is an interval of length h. It follows from property 9. Okay, so this. So going from, let's see. How come they didn't apply the h to the center? Table 5.5. Do we have 5.5 ready to go? No, I think that was in the last section. Let me see if I think I have it here. 5.5. Let's see, I think I have it. Let's go back. We did 5.3 today. So I think it's in 5.2. Theorem. Just pulling up here this table. Okay, right here. Come on. I was kind of bugging a little bit. So we have this table 5.5, additional properties of integrals. If x is positive, then the integral is going to be positive. If f is greater than, here it is. If f is between little m and m, then m times, okay, so it's an interval. Oh, okay. So that was a property on this table here. Trying to, it won't let me just keep it over here. But it says if f is between m and m, then m times b minus a is between that, which is between big M times b minus a. And in our context, b minus a is just h for that example that we're working on, right? So that makes sense. Okay, so that was a direct application of it from that table. Okay, so then right, where'd it go? This guy here comes from the table. So when we have this property going on, then the b minus a is just h in this context, right? So m times h is going to be less than or equal to this, which is less than or equal to this. And then we can divide all three parts by h. So if we divide all three parts by h, again, this is just going to be this. Divide all parts by h, we get this. Then we take the limit as h tends to 0 of all the parts. Notice that there's no h on the left, there's no h on the right. So then those become, should just be m, or f of x. And that's going to be the derivative. Where is it? Okay, so by the squeeze theorem, we conclude that a prime exists and a is differentiable, all right? So because this is differentiable, this exists and is differentiable, this exists, then this derivative has to exist. It's something like that. Let's see, by the squeeze theorem in 2.5, we conclude that a prime exists and is differentiable. This is a number because there's no h, so that's going to be just m, little m. This is going to be big M. So this derivative has to exist. Having established that the area function a is an antiderivative of f, we know that the area function f of x is going to be the area function a plus some constant, where f is any antiderivative. Noting that a of a is 0, it follows that f of b minus f of a, which is going to be, so I think we said that, okay, this is going to be a of b plus c minus a of a plus c. We're just doing a direct application of this guy here. So I think this goes to 0, a of a goes to 0, because it's like the area under the curve at a point. These c's are essentially going to cancel each other out, and so this all condenses down to just a of b. But then a of b in terms of the definite integral is going to be the integral from a to b of this, which is going to be f of b minus fa. Which is part 2 of the fundamental theorem. Okay, that's interesting, you know. So, you know, we did the best we could. Hopefully, you know, it is what it is. I think I've assigned homework sets for this. Just go through the homework, do the best that you can, okay? Like, that's why I loaded things as early as I could, including the final. This stuff is up. So what that means is that you can kind of be working on it. You can be practicing. You can be practicing. You can work together. You can work on it with the tutor. I just want you to think about it. I want to expose you to it. You know, I'm available. You know, if you want to work through it with me, I can do Zoom calls and all that too. But you know, so that's essentially the last of the new material that I wanted to go through for this quarter. I think I will go back and do a bonus lecture for section 4.9 because I just want to see what's there. You know, I don't get an opportunity to teach this course often, so I was excited to do it because this is really my favorite. I really do like it. I know I stammered a little bit towards the end, but that's just how it goes sometimes. But it's a lot of fun to me and it's near and dear. Let's see. So yeah, all the remaining assignments are posted for the rest of the quarter. Okay, so I'm just trying to give everyone time. We have about a little over a week remaining. All assignments are due next Saturday. Okay, so we can access any old exam, any old homework, any old quiz. I reduced the late penalty from 20% to 10%. So if you really want an A on any assignment, honestly, you can go back and get it. It's just a matter of getting, you know, achieving the score and submitting the assignment. And I'm available for questions. Be sure to also submit your what is it called? Course evaluations or surveys. I think you should have gotten an email about that. Okay. So it's been a very interesting quarter. I'm available. I'm just going to I'll be in communication via the announcements tab in Moodle, and I'll just be monitoring everybody's progress via Pearson. Okay. And on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace. I'm proud of you guys. I'm happy for you. Keep your head up. Stay strong. Like, that's no small feat. Y'all just did calculus during the pandemic. Like, if that's not a testament to your divinity, I don't know what is, right? Again, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Peace. Star Child. All right.